Hey everybody, today we are going to talk about geometric solid figures, and we're specifically going to talk about polyhedra, which is plural for polyhedron. We'll talk about the numbers of faces, vertices, edges. We'll talk about Euler's theorem, and we will talk about cross sections of polyhedra. So first, a polyhedron is a solid that is bounded by polygons that enclose a single region of space. So I'm going to show you some examples of polyhedra. So this one right here, this is a cube. And here we have a rectangular prism. Okay, so we've got a cube and a prism. I've got another prism here. It's another rectangular prism. I've got a couple triangular prisms. So these are triangular prisms. I have some pyramids. So I've got a pyramid here. On the pyramid I've got here, the base is a square. So this is a square pyramid. Here's a pyramid whose base is a triangle. So this is a triangular pyramid. Here's another prism. This prism has a base that is a hexagon. So this is a hexagonal prism. Okay, now I've got one more cube here. Okay, so everything is a square of the same size, so that's a cube. Okay, now I'm going to show you a few things that are not polyhedra. Okay, so it's still a geometric solid, but you notice that this one has some things on it that are not polygons. This circle is not a polygon, so this is not a polyhedron. Okay, so then I've got a cone. So a cone has a base that is a circle. That is not a polygon, so a cone is not a polyhedron. Here is another cylinder. It's got circular bases, so it's not a polyhedron. Here's a sphere. A sphere does not have any polygons, so it is not a polyhedron. And last, I have a half sphere or a hemisphere, and it's got a base that is a circle, so it is not considered a polyhedron. So we want to recognize what is and what is not a polyhedron. In order to be a polyhedron, it must have polygons for every side. Okay, so a face of a polyhedron is a polygon. So the faces are the polygons. Okay, so we'll look at this one right here, this prism. It's got a triangle here, it's got a triangle here, and then it's got three rectangles. Those are all faces. So every polygon on it is called a face. An edge is a line segment formed by the intersection of two faces. So where two faces come together here, we have a line segment, and that line segment is called an edge. A vertex is a point where three or more edges meet. Okay, so right here, I've got 1, 2, 3 edges meeting at that corner. That corner is called a vertex. Now, it could be more than just 3 that meet at one spot. For example, on this prism here, I've got 1, 2, 3, 4 edges meeting all right here at this one point. Okay, so it has to be at least 3, can be more. A base is a polygon that is used to name a polyhedron. Okay, so now on this prism, I don't name it based on the rectangles. Every prism has rectangles on it. Okay, but there are 2 parallel and congruent hexagons on this prism. This is called a hexagonal prism. Okay, so the bases are the hexagons. Here's another prism. I'm not going to use the 3 rectangles. I'm going to use the triangular base. Okay, so if there's a prism that has anything other than a rectangle, that rectangle is the base. So this is a triangular prism. the base is a triangle. Okay, so here's another rectangular prism. Here's a pyramid whose base is a triangle. This is a triangular pyramid. A regular polyhedron is a polyhedron whose faces are all congruent, regular polygons. Okay, so that means every face on the polygon is exactly the same, and they are all regular polygons. A cube is one example. Okay, a cube has 6 squares. A square is a regular polygon because all the sides are congruent and all the angles are congruent. And a cube also has all those squares exactly the same size. Okay, so the polygons are regular, and all 6 polygons on here are congruent to each other. So a cube is a regular polygon. A regular polyhedron. A convex polyhedron. Every polyhedron I have shown you today is convex because it has no sides that are caved inward. All the vertices point out, not in toward the center of the polyhedron. The Platonic solids, named after Plato, they are 5 different regular polyhedra. Now, not every polyhedron can even be made regular. There are 5 of them that can. There's the tetrahedron, and I have one here that is close to a regular tetrahedron. Okay, so this one right here is close, but not quite. I've got 3 congruent triangles. This one on the base is not quite congruent. Its sides are a little bit smaller, but if you can imagine this right here having all 4 triangles exactly the same size, then this would be a regular tetrahedron, in which case it would be one of the Platonic solids, but it's not quite regular. Notice that tetra, meaning that it has 4 sides, like the game Tetris. Every piece in that game has 4 little squares on it. A cube. A cube is a regular polyhedron. I've got 2 of those here. So these are regular polyhedra, which means they qualify as one of the Platonic solids. The regular octahedron, so that's going to have 8 polygons on it. A regular dodecahedron would have 12 polygons, and a regular icosahedron would have 20. And our last vocabulary term here is cross-section. That is the intersection of a plane and a solid. Okay, so I've got here a cube and a rectangular prism, but we'll put them together as though they are one rectangular prism. And if I was to slice through right here and then look at what I'm shown on the inside, I see a square. That square is a cross section. Now, we don't have to slice directly like that. We could slice diagonally down one of the sides, so I could slice like that, and I would get a rectangle. I could slice in all different ways. In this case, though, the only option I have to show you is slicing this way, and what we see where we sliced is called a cross section. Okay, so in our next section, we are going to determine what is and what is not a polyhedron. So here, tell whether the solid is a polyhedron. If it is, name it and find the number of faces, vertices, and edges. Everything on this one is a polyhedron. So yes, it is a polyhedron. Okay, so then we will name it. Okay, so this is a prism because it's got 2 bases that are parallel and congruent to each other. And all sides on this are rectangles, so it is a rectangular prism. Okay, so next we're going to count the faces, vertices, and edges. So the number of faces, that's all of the polygons that are on this thing. I've got one here in the front and one in the back. and then I've got a top, a bottom, a left side, and a right side for a total of 6 faces. Okay, the vertices, those are all the corners. So we're going to count all the corners. I've got 1, 2, 3, 4, 5, 6, 7, 8 vertices. And then the number of edges, that's all of the line segments. So I've got 4 edges around the front and 4 around the back. And then I've got 1, 2, 3, 4 more. So that's 4, 8, and then 12 edges. Okay, then for B, is it a polyhedron? Everything on it is a polygon. So yes. So yes, it is a polyhedron. Okay, what kind? Now it's got a single base, and then all of the other faces meet at one point, at one vertex. So this is a pyramid. The base has 1, 2, 3, 4, 5, 6 sides. That's a hexagon. So this is a hexagonal pyramid. Okay, so now we want the number of faces, vertices, and edges. So for faces, we've got 1 on the bottom, the hexagon, and then we've got some triangles. So I've got this one in the front, and then we'll count our way around. So the base is 1, this one right here in the front is 2, 3, and the little one we can't see much of here is 4, and the back is 5. Little one here is 6, and then right here is 7. It has 7 faces. The number of vertices, all the corners around the base, it's a hexagon, so I've got 6. 1, 2, 3, 4, 5, 6. And then I've got 1 up here. It has 7 vertices. Then the number of edges. Okay, the base is a hexagon, so it's got 6 here. Then it's going to have 6 more that go toward that vertex. So I've got 6, 7, 8, 9, 10, 11, and 12 edges. Is this one right here a polyhedron? Well, it's got a circle on it, so the answer is no. This one actually has a name. This is a cone, but it is not a polyhedron. So we say no, and we move on to the next row where I see a pyramid. This is a polyhedron because all of the faces are polygons, so yes. It's a pyramid just like this one here, except this one had a hexagon for a base. This one has a square. This is a square pyramid. Okay, so then we count the number of faces, vertices, and edges. So for faces, it's got 1 here on the bottom. That's the base. And because it's a square, it's got 4 sides. That means it's going to have 4 more triangles. So that's a total of 5 faces. Vertices are all the corners, 1, 2, 3, 4 around the square, and 1 up here for a total of 5 vertices. And then the number of edges, 4 around the base, 5, 6, 7, and 8. This next one has a rounded edge. No, it is not a polyhedron, and we'll move on. Everything here is a polyhedron, so the answer is yes. This is a type of prism because everything, because it doesn't go to one vertex like this, and because everything around this side is a rectangle, but then on these 2 ends we have triangles. So this is a triangular prism. Okay, so then we will count the number of faces, vertices, and edges. Okay, so it's got 2 triangles for faces. Then it's got 3 rectangles wrapping around them for a total of 5 faces. The number of vertices, it's got 3 vertices around this base, and it's got 3 vertices around this base for a total of 6 vertices. Then edges, it's got 3 edges around this base and 3 edges around this base. That's 6, 7, 8, and 9 edges. Okay, now Euler figured out that every time for every polyhedron, the number of faces plus the number of vertices is always exactly the same as the number of edges plus 2. So faces plus vertices is 2 more than the number of edges, and we should see that working out here. Faces plus vertices, 8 plus 6 is 14. That's 2 more than 12. 7 plus 7 is 14. That's 2 more than 12. 5 plus 5 is 10. That's 2 more than 8. And 5 plus 6 is 15. 15, that's not 15. 5 plus 6 is 11. I added the 6 and the 9, I think, in my head there. 5 plus 6 is 11, and that is 2 more than 9. So it's always true that the number of faces plus vertices is 2 more than the edges. All right, so let's find the number of edges on the frame of this house. Okay, so we've got a base here. That's 4 edges. Okay, then we have these uprights on the corners. That's another 4. 5, 6, 7, 8, 9, 10, 11. And I'm not sure if I counted that correctly, so let's try that again. So we've got 1, 2, 3, 4 around the bottom. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So I'm saying the number of edges is 15. Now, let's confirm that by using Euler's theorem. So let's actually find the number of faces and the number of vertices. Okay, so I've got a face here. It's a pentagon. And a face over here that's also a pentagon. Okay, so that's 2. And then, because they're pentagons, that means I'm going to have 5 rectangles, including this one on the bottom here. 5 rectangles wrapped around that. So that's going to be a total of 7 faces. So for faces, I'm counting 7. For vertices, I've got 1, 2, 3, 4 around here. So 1, 2, 3, 4 vertices here. Okay, so then 5, 6, 7, 8, 9, and 10 vertices. Okay, so now let's plug that into Euler's theorem and see if it worked out. Faces plus vertices is edges plus 2. So that's 7 plus 10 equals 15 plus 2. And that's 17 equals 17. So that makes me reasonably certain that my numbers are all correct. Now what it said here is find the number of edges, and that is 15. Now on this figure here, we are going to find the number of faces, vertices, and edges. This is a regular octahedron, so this is one of the Platonic solids, one that I didn't have to show you before. Okay, so we'll find faces, vertices, and edges, and then we will check our answer to make sure it fits into Euler's theorem. Okay, so the number of faces. Now this right here doesn't count because it's not on the surface. So it's going to be the 4 triangles around the top and the 4 triangles around the bottom that are on the surface. So it has 8 faces. Vertices, 1, 2, 3, 4, 5, and 6 vertices. And then edges. Okay, so it's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 edges. Now let's see if that works in Euler's theorem. So faces plus vertices equals edges plus 2. So 8 plus 6 equals 12 plus 2. 8 plus 6 is 14. 12 plus 2 is 14. So I can be reasonably certain that my number of faces, vertices, and edges is correct. And next we are going to look at some cross sections. So we'll describe a shape formed by the intersection of a plane and a cube. And the next line, so this is all cubes. The next line here will not all be cubes. Okay, so here we have a cube intersected by a plane parallel to the bases. And it makes this cross section right here. This is a square. Okay, now I know the angles don't look like 90 degrees, but it's kind of a perspective thing when you're looking at three-dimensional figures placed onto a two-dimensional piece of paper. Okay, so here's a cube sliced diagonally, and this is the cross section. It is a rectangle. And then here we have a cube kind of from the top to the bottom, but not perpendicular to the bases. That forms a cross section that is a trapezoid. Here's another cube with the corner cut off. There's the cross section. That is a triangle. Here's a cone cut by a plane parallel to the base. That cross section is a circle. And here is a hexagonal prism that is sliced between the bases, parallel to the bases, and we get a hexagon for a cross section.